Good evening. Today we're going to be going over one of the applications of the derivative. Specifically, we're going to use derivatives to find a maximum or a minimum in a three-dimensional object. Our objective today is to take a flat square piece of material, as denoted by the outside white lines there, and make a three-dimensional rectangular prism or a box out of this material. We're going to do that by cutting out a smaller square out of each corner. Squares that we're going to cut out of each corner are shown by the purple lines. We're going to label the length of the large squares as x, and each side of the small square is going to be length a. So after we cut out the squares, after we cut out a, we're going to have a flat shape that looks something like this. Dimensions are shown. You'll notice that the length of each side of your base, so your length and your width of your box, is going to be x minus 2a, because you have to take out an a on each side of the long square. And your height of this box, of your prism, is going to be simply a. So therefore, whenever we take that and fold it up, we're going to get a shape that looks like this. Okay? Now, how do we go about maximizing the volume of this box? If we make A large, the box is very tall, but the base is very small. It almost becomes like a long tube. It's rectangular shaped. If we make A small, it's like a flat pan that doesn't have very much depth. So common sense tells us that the answer kind of has to be somewhere in the middle. But how do we go about proving that mathematically? Well, that's what we're going to do. Okay, first off, we have to come up with an equation for the volume of our box. So if you remember, the volume of a rectangular prism is simply the length times the width times the height. Okay, in our case, our length was x minus 2a, our width is also x minus 2a, and our height is a. That gives us an overall volume of x minus 2a squared times a. Now, one of the applications of the derivative is that we can actually set it equal to 0 and find a local minimum or a local maximum. So that's what we're going to do. We're going to take the derivative of our volume equation and set it equal to 0 and then solve for the solution. So now we need to go about finding the derivative. If you don't recall how to take derivatives, you can review some of the earlier videos in our lecture series. Alright, so in order to take the derivative of this, we're actually going to go ahead and expand it all the way out algebraically. So let's expand what's inside the parentheses first. So x minus 2a squared is going to give us x squared minus 4xa plus 4xa squared. And then that'll be multiplied times a. We distribute the a through and rearrange it so the a is our variable of interest. We're going to arrange the a so the a's exponential is in decreasing order, just for formation's sake. And that gives us 4 4a cubed minus 4xa squared plus x squared a. So now we're going to take the derivative of this volume equation, now that we have expanded it out into a form that we can actually take the derivative of, and set that equal to 0. So the derivative of our volume equation is 12a squared minus 8xa plus x squared. Alright, now this is a quadratic form. Our variable of interest here is a. You notice that I differentiated with respect to a because a is what we're actually changing. We can assume our x is going to be constant. So, if you remember the quadratic formula, because we can't factor this equation very easily in our heads, so we're going to have to use an alternate method to solve it. The quadratic formula is such that any equation that takes on the form ax squared plus bx plus c equals 0, you can actually solve for x by the following. Negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, now in our particular equation, we're going to change our x's in the quadratic form of the general equation. Those are going to be replaced by our little a's, and therefore our large A for this one is simply 12. B is negative 8x, and C is x squared. Okay, so now we're going to set our derivative equation equal to 0 and solve for A using the quadratic formula. So therefore, A is going to be equal to 8x plus or minus square root of negative 8x squared minus 4 times 12 times x squared all over 2 times 12. Now, it's just a matter of algebra. A is equal to 8x plus or minus square root of 64 x squared minus 48 x squared over 24. That further simplifies down to 8x plus or minus square root 16x squared over 24. Which is 8x plus or minus 4x over 24, which is going to equal 12x over 24 or 4x over 24. That simplifies down to 1/2 x or 1/6 x for a final answer. Notice that this problem has two solutions. One is going to be a minimum, and one is going to be a maximum. Most people gravitate toward A equals 1/2 x to be a maximum. However, if we plug it into our original volume function, remember our original volume function was V equals x minus 2a squared times A. If we substitute in 1/2 x for A into this equation, we actually see that this part of the equation is equal to 0. So therefore your volume is equal to 0. That means it's a minimum. If you think about this logically, it does make sense. If we did that, and x was equal to 1/2, or yes, A was equal to 1/2 x, we would actually get this scenario here, where we'd have 0 base. You would cut out every single corner of your square. So therefore, the correct answer that provides a maximum volume is A equal to 1/6 x.